Okay, good morning. Welcome to this next lecture. We are doing the velocity field calculation, okay, using our branch cut contour. So we reach this position where we are seeing that one part of the contribution to the velocity field of the plate is due to a continuous range, an integral, okay, over the wave number from 0 to infinity. Okay. So now this integral, the way it is, this integral cannot be computed in closed form. Okay. It has to be done numerically, okay. But here we are going to find some approximate value to it, okay. So the contribution V1 plus V2 is given by, okay. So if I take the minus I and I get a plus. So I get omega f, okay. Then this mu is a constant, Kp fourth is a constant, mu Kp fourth, okay, divided by this 2 cancels with this 2, so I get pi b. Then the integral 0 to infinity, okay. Then gamma plus is there, so k square minus k0 square to the power half, okay, e to the power minus ux du divided by k fourth minus kp fourth whole squared into k square minus k0 squared minus mu square kp8. Okay, we should not forget that k has to be k0 plus iu, okay. So k comes here, k comes here, k comes here, so I am not changing that, it will become horrendous, okay. Now we will find as x tends to infinity, x approaches infinity, that means I have this 1D plate, okay, excited by a line force. So I have some vibrations happening, some sound field being generated and so forth, and the sound field is interacting. So as I move far away from my source, as x tends to infinity, I want to see the velocity field. Okay. So let us not forget that my total velocity field, just want to remind here, is first of all the sum of residues which we are yet to calculate, okay, plus V1 plus V2. So we are looking at V1 plus V2 only now. This residue part has not come in yet, okay, we will do that. Okay, we will do the residue part a little later. I said that is a separate study, okay. So we are looking at V1 plus V2, and V1 plus V2 is this integral, and I say that this is not integrable in closed form. So we see what happens as you move further away from the forcing, okay. Now we have e to the power minus ux in the numerator. So as x tends to infinity, this goes to 0, okay, this goes to 0. As x tends to infinity, this goes to 0. And so as x tends to infinity, the dominant contribution comes from u equal to 0. Okay. So I had said my k is equal to k0 plus iu, and so if u happens to be equal to 0, my k should be equal to k0. Okay. So in here k will be equal to k0 or close to k0, and k will be equal to k0 here. So in the approximate sense, I will have e to the power minus ux by the denominator polynomial given by e to the power of minus ux by minus mu square kp8. Okay. So this part and the denominator we write as this. Okay. So there is still this portion. So what do? Now we have the V1 plus V2 is equal to omega f mu kp fourth by pi b, okay, minus mu square kp 8, okay, integral 0 to infinity. In here I will substitute k as k0 plus iu, so k square plus twice I k0 u minus u square minus k0 square to the power half e to the power of minus ux du. That's about it. So this cancels off. Okay. So I get this whole thing minus omega f by pi b mu kp fourth okay, integral 0 to infinity square root of twice I k0 u minus u square, okay, e to the power of minus ux du, okay, and for small values of u is tending towards 0, okay. So I get minus omega f by pi b mu kp fourth, okay, and this u is a small quantity, so u square I am going to ignore. Then I will get outside square root of 2k0, this and this, and inside 0 to infinity iu to the power half e to the power of minus ux du. Okay. Okay. So somewhere down the road we forgot e to the power of I k0 x, e to the power of I k0 x. Okay, so e to the power of I k0 x. Okay, and so if we look at this part now, if we look at this part, okay, let us see. Okay, here also we forgot, yeah, this, okay, e to the power of I k0 x. If you look at this part will be an integral which decays as x to the power minus 3 by 2 after you integrate. Okay, so there is a wave which has a dominant wave number as k0, okay, on the plate, but it decays away as you move towards infinity at the rate x to the power minus 3 by 2. Okay, so we have to weigh this contribution along with the other contributions from residue. So which one is big, which one is small, so forth. Okay, but the integrals from the cut, the vertical cut on the left and right side at k0 gives me this part, this behavior gives me this behavior. Okay, so that's one major part of it done. We still have to deal with residues, that will deal, okay, residues. Okay, now let us see, we have to move towards the thought about singularities. Okay, singularities. So that we can get the residue contributions, which is very important. Okay, so now to move towards that, first of all we need to non-dimensionalize. Okay, non-dimensionalize. Okay, so denominator at some point we had k fourth minus kp fourth into square root of k square minus k0 square minus mu kp fourth. Okay, this was the denominator. Okay, so we will, cutting short the entire discussion, we need one parameter which is non-dimensional frequency, we need. Okay, the second is a non-dimensional material parameter which can take material properties like fluid density, speed of sound, plate density, okay, and any other parameters, so that we can weigh that when fluid is heavy, how it behaves, if fluid is light, how the situation looks like, and from here at high frequencies or low frequencies or around some typical frequencies. So these two parameters we need. Okay, so now to refresh you, the coincidence frequency in these plate problems is given by m mass per unit area c fourth by B. C is the speed of sound in the material, B is the flexural rigidity. Okay. Now we will take a value or a parameter called M, which is K0 over Kp, okay, the acoustic wave number by the plate wave number. And if you look at this, this is omega by C0 by omega by Cp, okay. So that becomes equal to Cp by C0, or let me keep it as C, speed of sound in the medium, Cp by C, okay. So if we now elaborate okay, if we now elaborate here, K0 is omega by C and Kp is m omega square by B to the power 1/4. Okay, so let me take out onto the next page. Okay, so M, which is equal to K0 by Kp, is equal to 4th root of B by M omega square into omega by C. Okay, this is equal to what? 4th root of square root of B by M omega square, and I take 4 times of this inside, omega 4th by C 4th. Okay, so this is equal to 4th root of B omega square by M C 4th. Okay. Now this quantity from the previous page is omega C squared, the denominator. Okay, so this is equal to 4th root square root of omega square by omega square C, coincidence frequency, and therefore this is equal to omega by omega C. Okay, so this is the non-dimensional frequency parameter. Okay, the other material non-dimensional parameter epsilon, let me write it, okay, as rho, the fluid density, speed of sound by mass per unit area of the panel into coincidence frequency. Okay, this is the other parameter. Okay, so these are the two we need. Okay, there is a discussion behind it and so forth, but these are the two we need. Now if you recall, somewhere in the derivation, okay, of the plate in the Fourier domain, okay, in Fourier or wave domain, we came up across this equation, which is B K 4th minus m omega square into v of k, okay, is equal to minus I omega f, okay, minus omega square rho phi of k comma 0. Okay, you might recall if we go back to the derivation. Okay, now you should know that this term comes from plate stiffness, right? B is flexural stiffness, plate stiffness. Okay, and this term comes from plate inertia, plate inertia. Okay, and if we take B out, okay, suppose we take B out and divide, okay, so I take B out, I get k fourth minus m omega square by B, which is k p fourth into V of k. Okay, this is still plate stiffness, this is still plate inertia, okay, and divide by B. So if I divide, I get minus I omega f by B minus omega square rho by B phi k comma 0. Okay, and phi k comma 0 was minus Vk, this was minus of Vk by gamma, if you recall. So this is going to be equal to minus I omega f by B plus omega square rho by B V of k by gamma. Okay, now about gamma, let us see about gamma. Okay, now how did we formulate the 2D wave equation for the potential? We get minus k square phi in the Fourier domain with x and then y plus del 2 phi by del y square k comma y, okay, plus k 0 square phi of k comma y is 0. This is what we got. Okay, then we have del 2 phi by del y square into k comma y minus, okay, k square minus k 0 square phi of k comma y. Okay, so this carries information about the speed of sound, hence compressibility, of the fluid, and this term comes from del 2 phi by del x square, which is similar to del 2 p by del x square. Okay, so that the net pressure across an element. Okay, okay, so this term we will consider to be representing pressure. Okay, and this term to be representing compressibility. Okay. So we have structural stiffness, structural inertia, and a gamma over here, okay, and omega rho over here, so which is fluid density. Okay. So what do we get as a in the net? So we'll get let's see, k fourth minus kp fourth into v of k is equal to minus I omega f by b plus omega square rho by b v of k by gamma, and I take v of k to the left, k fourth minus kp fourth minus omega square rho by b gamma, okay, into v of k is equal to minus I omega f by b. Then k fourth minus kp fourth into gamma minus, let me say, omega square m by b rho by m, okay, into v of k by gamma, let's say, is equal to minus I omega f over b. Okay. So that my v of k is equal to minus I omega f gamma by b, okay, and this part comes down here, k fourth minus kp fourth into gamma minus m omega square by b is kp fourth, rho by m is mu. Okay, so this is my denominator now. This is my denominator. So denominator carries the roots of the system. Okay, we are going to do contour integration. So roots of the system or poles of the system are important. So now we have already seen k fourth comes from plate stiffness, kp fourth comes from plate inertia, then here square root of k square, this comes from fluid pressure, minus k0 square, this comes from fluid compressibility, and minus kp fourth mu carrying rho, this is fluid inertia. Okay. When the plate was in vacuum, it was a play between plate stiffness. The behavior was a play between plate stiffness and plate inertia. But now that this is a coupled problem, it's a play between these 5 factors: 1, 2, 3, 4, and 5. These 5 factors come in various frequency regimes and various parameter regimes. They become more or less important. Okay, so I'll close it here. We'll continue this from the next class. Thanks.